Welcome to our presentation on the system architecture design of our hybrid edge cloud computing solution. We'll delve into how we've integrated edge and cloud technologies to create an efficient, scalable, and reliable system for industrial applications. Our hybrid edge cloud architecture leverages the strengths of both edge computing and cloud computing. At the edge, devices perform real-time data acquisition and initial processing right where the data is generated, close to the industrial machines. This proximity reduces latency, allowing for immediate monitoring and control. Meanwhile, the cloud handles heavy computational tasks, such as advanced analytics and long-term data storage. This division of labor not only optimizes bandwidth usage by pre-processing data at the edge but also ensures that we can scale our resources horizontally in the cloud to meet increasing demands. Moreover, this architecture enhances system resilience. Edge devices can continue to operate and collect data even during network disruptions, ensuring uninterrupted processing and minimal downtime. Let's break down the components of our system. First, we have the industrial machines equipped with various sensors and actuators. These sensors measure critical parameters like temperature, pressure, vibration, and energy consumption. We use the Modbus protocol over RS485 for reliable and robust communication in industrial environments, ensuring accurate data transmission from these machines to our edge devices. Next is the edge computing device. A robust, industrial-grade unit with a multi-core CPU and at least 4 GB of RAM. It's powered by a lightweight and secure operating system like Ubuntu Server or Debian. On this device, we run Node-RED to orchestrate data flows and integrate various protocols. We also utilize MQTT for efficient messaging between the edge and the cloud, and Modbus libraries to communicate with the industrial machines. A local database, such as SQLite or InfluxDB, is used for temporary data storage, which is crucial for buffering data during network interruptions. Our communication network employs MQTT for lightweight, efficient messaging and HTTP/REST APIs for configuration and control tasks. To ensure data security during transmission, we implement TLS/SSL encryption. In cases where additional security is needed, VPNs can be established to protect data over public networks. In the cloud, we leverage scalable compute services to run heavy analytics and machine learning models. Storage services like AWS S3 or Azure Blob Storage provide long-term data retention capabilities. For data analysis and visualization, we utilize tools like Grafana and other cloud-based analytics platforms. RESTful APIs facilitate interaction with external systems and applications, allowing for seamless integration and interoperability. Finally, the user interface is where data becomes actionable insights. Grafana dashboards offer real-time monitoring and historical data analysis, enabling users to visualize key performance indicators effectively. Additionally, our system includes alerting mechanisms that send notifications via email, SMS, or messaging apps to keep stakeholders informed about critical events. The process begins with data acquisition. Sensors attached to industrial machines collect real-time data. This data is transmitted over Modbus via RS485 to the edge computing device, ensuring a reliable and timely transfer of information. At the edge device, Node-RED processes the incoming data. Initial anomaly detection algorithms run here to identify any immediate issues. The pre-processed data is then stored temporarily in the local database, which serves as a buffer in case of network disruptions. Relevant data is securely published to the cloud using MQTT with TLS/SSL encryption. This ensures that sensitive information remains protected during transmission. In the cloud, data is ingested into scalable storage solutions. Advanced analytics and machine learning models process the data to extract valuable insights, which are then stored and prepared for visualization. Finally, Grafana dashboards present both real-time and historical data to users, enabling informed decision-making. If any anomalies are detected, either at the edge or in the cloud, alerts are generated based on predefined rules, ensuring that the right people are notified promptly. Security is a paramount concern throughout our system. We implement robust authentication and authorization protocols, such as OAuth 2.0 and JWT, to verify devices and users accessing the system. End-to-end encryption safeguards data both in transit and at rest, using industry-standard TLS/SSL protocols. Furthermore, we employ network security measures like firewalls and intrusion detection systems to protect against unauthorized access and cyber threats. These layers of security ensure the integrity, confidentiality, and availability of our system. In summary, our hybrid edge cloud architecture efficiently bridges the gap between real-time data processing and advanced analytics. By thoughtfully integrating edge devices, robust communication networks, scalable cloud services, and user-centric interfaces, all underpinned by strong security measures, we've developed a system that's not only powerful and flexible but also secure and reliable for industrial applications. Next, we'll delve deeper into the operating system and software stack that powers our edge computing devices. We'll explore the operating system and software stack that power both our edge devices and cloud infrastructure. These components are the backbone of our system, enabling efficient data processing, secure communication, and seamless integration between the edge and the cloud. At the core of our edge devices, we've chosen to deploy either Ubuntu Server or Debian as the operating system. These Linux distributions are lightweight and widely supported, making them ideal for embedded devices. We prioritize security by ensuring regular updates and applying security patches promptly. Unnecessary services are disabled to minimize potential vulnerabilities and optimize system performance. Node-RED serves as the orchestration engine on our edge devices. This powerful, flow-based development tool allows us to seamlessly connect devices, integrate protocols, and manage data flows. We leverage Node-RED's flexibility to develop custom nodes or utilize existing ones for protocols like Modbus, MQTT, and HTTP, facilitating smooth communication between industrial machines and cloud services. To communicate with industrial machines using the Modbus RTU protocol over RS485, we integrate Modbus libraries into our system. This can be achieved through Node-RED Modbus nodes or Python libraries like PyModbus when additional customization is required. These libraries handle the complexities of Modbus communication, allowing us to reliably transmit and receive data from our industrial equipment. For efficient messaging between the edge and the cloud, we utilize the MQTT protocol. On the edge device, we deploy a lightweight MQTT broker such as Mosquito or EMQX. Node-RED's MQTT nodes act as clients, enabling us to publish and subscribe to specific topics. This setup ensures low latency, reliable communication with minimal overhead, which is crucial for real-time data processing. To handle temporary data storage on the edge device, we use a local database. Depending on our needs, we might choose SQLite for its simplicity and minimal resource consumption, or InfluxDB if we require specialized time series data storage. This local storage acts as a buffer during network outages and supports local analytics, ensuring that no critical data is lost and operations can continue uninterrupted. An essential feature of our edge computing is the ability to perform real-time anomaly detection. We implement this through Node-RED function nodes, where we can code custom algorithms using statistical methods. For more advanced detection, we integrate lightweight machine learning libraries optimized for edge devices. This enables us to identify and respond to irregularities promptly, enhancing system reliability and safety. Security is a top priority. On our edge devices, we employ firewalls like UFW or IPtables to control network traffic and prevent unauthorized access. For secure communications, we use encryption libraries such as OpenSSL, ensuring that data transmitted to and from the edge device is encrypted and protected against eavesdropping and tampering. In the cloud, we harness the power of leading providers like AWS, Azure, or Google Cloud Platform to run our compute services. We utilize serverless functions such as AWS Lambda or container services like AWS ECS for scalability and efficiency. These services allow us to perform heavy computations, run advanced analytics, and deploy machine learning models without the overhead of managing physical infrastructure. For data storage, we use managed databases like AWS RDS or DynamoDB for structured data. For time series data, we might opt for InfluxDB Cloud. Large datasets and unstructured data are stored in object storage solutions like AWS S3. These services offer scalability, durability, and easy access, ensuring that our data is securely stored and readily available for processing. Advanced analytics and machine learning are critical for extracting actionable insights from our data. We leverage services like AWS SageMaker or Azure ML to build, train, and deploy sophisticated models. These tools enable us to perform advanced anomaly detection and predictive maintenance, helping us anticipate issues before they occur and optimize operational efficiency. Visualization is key to making sense of complex data. We host Grafana on our cloud infrastructure, connecting it to our databases to provide real-time and historical data visualization. Grafana's customizable dashboards allow different user roles, such as engineers, managers, and operators, to access the specific insights they need, enhancing decision-making across the organization. To facilitate interaction with external systems and applications, we implement RESTful APIs managed through an API gateway. This setup provides a scalable and secure interface for data exchange. We strengthen security by implementing authentication services like OAuth 2.0 and integrating with Identity and Access Management (IAM) services offered by our cloud provider. This ensures that only authorized users and devices can access our system. Next, we'll delve into the critical components of data acquisition and the communication protocols that enable seamless connectivity in our hybrid edge cloud system. Effective data acquisition and reliable communication are the backbone of our solution, ensuring that information flows efficiently from industrial machines to actionable insights. Let's start with the integration of Modbus over RS485, a fundamental aspect of our data acquisition process. Modbus is an open, serial communication protocol that's widely used in industrial environments due to its simplicity and reliability. It allows multiple devices to communicate over a single network, making it ideal for connecting various sensors and machines. The RS485 interface complements Modbus by providing a robust serial communication standard capable of long-distance and noise-resistant data transmission. This is especially important in industrial settings where electrical interference is common. The first step is establishing the hardware connection between the industrial machines and the edge device. We utilize either built-in RS485 ports on the edge device or USB to RS485 converters when necessary. Proper wiring is crucial. We ensure that the network is correctly terminated and grounded to prevent signal reflections and minimize electrical noise. This attention to detail enhances communication reliability and data integrity. Next, we configure the Modbus network. Each connected device is assigned a unique Modbus address to facilitate clear communication and prevent conflicts. We set communication parameters such as the baud rate, commonly at 9,600 or 19,200 bits per second, and configure parity and stop bits according to the device specifications. These settings must be consistent across all devices on the network to ensure smooth communication. Software integration is handled through Node-RED, where we install the Node-RED Contribution Modbus package. We configure Modbus read and write nodes with the appropriate parameters, allowing us to interact with the industrial machines directly from our edge device. To ensure robustness, we implement error handling mechanisms such as retries and monitor for exceptions like timeouts or cyclic redundancy check (CRC) errors. This proactive approach helps maintain continuous communication even in the face of transient issues. The data received from Modbus devices often requires parsing and formatting. We map Modbus registers to meaningful sensor data, converting raw values into usable information. This involves handling different data types, such as integers and floating point numbers, and addressing byte order considerations. By accurately interpreting the data, we ensure that subsequent processing and analysis are based on correct and meaningful inputs. Throughout this process, we adhere to several best practices. Isolation. We use opto-isolated RS485 interfaces to protect our devices from voltage spikes and electrical noise, enhancing system durability. Diagnostics. Implementing diagnostic tools allows us to monitor Modbus communication health in real time, enabling quick detection and resolution of issues. Documentation. We maintain comprehensive and up-to-date documentation of all Modbus registers and configurations. This is essential for troubleshooting, future expansions, and ensuring that all team members have access to critical system information. Moving on to edge-to-cloud communication, we utilize the MQTT protocol, a lightweight, publish-subscribe network protocol ideal for IoT applications. Broker setup. We set up an MQTT broker to manage message distribution. This can be a local broker on the edge device for internal communication and a cloud broker, such as AWS IoT Core or Azure IoT Hub, for communication with cloud services. Topic structure. We organize our MQTT topics hierarchically, for example, Factory, Site 1, Machine A, Sensor 1. This structured approach allows for efficient data management and scalability as we add more devices and sensors to the network. Quality of service, QoS. To ensure reliable message delivery, we use MQTT's QoS levels. For critical data, we set QoS to 1, guaranteeing that a message is delivered at least once. Security. Security is paramount. We secure our communication channels with TLS/SSL encryption, protecting data during transmission. Authentication is handled using certificates or tokens, verifying the identity of devices before they can publish or subscribe to topics. In addition to MQTT, we employ HTTP RESTful APIs for specific use cases. Device provisioning. Adding new devices to the network securely and efficiently. Configuration updates, remotely updating device settings and parameters. Control commands, sending commands from the cloud to edge devices or machines. We implement these APIs using Node-RED's HTTP nodes, creating endpoints that can handle incoming requests. To secure these APIs, we use authentication methods like API keys or OAuth, ensuring that only authorized entities can access or modify device configurations. Data serialization formats are crucial for efficient data transmission. JSON is our go-to format due to its human readability and widespread support. It's excellent for interoperability between different systems and platforms. For greater efficiency, especially when bandwidth is limited, we use MessagePack, a binary serialization format that is more compact than JSON. To further optimize data transmission, we apply compression techniques like gzip when sending large payloads. This reduces the amount of data that needs to be transmitted, saving bandwidth and speeding up communication. Optimizing network usage is essential for system performance and reliability. Bandwidth optimization. We transmit only necessary data, filtering out redundant or non-critical information at the edge. Data aggregation techniques are used to combine multiple data points into a single transmission, reducing the number of messages sent. Offline handling. Recognizing that network connectivity can be intermittent, we implement local buffering to store data during connectivity issues. Retry mechanisms are in place to automatically attempt data transmission when the network is restored, ensuring that no critical data is lost. These strategies help maintain system functionality even in less than ideal network conditions, providing resilience and reliability. Next, we'll explore how our system processes data in real time at the edge and how we implement anomaly detection to ensure the reliability and efficiency of industrial operations. Effective data processing and timely anomaly detection are crucial for proactive maintenance and avoiding unexpected downtime. At the edge, data preprocessing is the first step to prepare raw sensor data for analysis and transmission. This involves several key techniques. Filtering. we remove noise from the data using methods like moving average filters or low-pass filters. This smooths out transient fluctuations and highlights the underlying trends. Normalization. Data is scaled to a standard range, ensuring consistency across different sensors and units of measurement. This is essential for accurate comparisons and analyses. Timestamping. Each data point is assigned an accurate timestamp. This is critical for synchronizing data from multiple sources and for time series analysis. In Node-RED, we orchestrate the data flow through a series of nodes. Input nodes. We use Modbus read nodes to acquire data from the industrial machines. Processing nodes. Function nodes allow us to apply custom processing logic, such as filtering, normalization, and initial analysis. Output nodes. Process data is then directed to MQTT publish nodes for transmission to the cloud and to local database nodes for temporary storage. This modular approach enables us to efficiently manage data processing tasks and adapt to changing requirements. Optimizing performance on the edge device is essential due to resource constraints. Efficient coding. We minimize the use of global variables to reduce memory usage and potential conflicts. Wherever possible, we employ asynchronous operations to prevent blocking the event loop, ensuring that the system remains responsive. Resource management. Continuous monitoring of CPU and memory usage helps us detect and address performance bottlenecks. We avoid blocking operations that could stall the event loop, such as long-running computations without yielding control. At the edge, we implement real-time anomaly detection using lightweight algorithms suitable for the device's limited resources. Statistical methods. Thresholding. We define acceptable ranges for sensor values. If a reading falls outside this range, it's flagged as an anomaly. Standard deviation. By calculating the standard deviation from the mean, we can detect significant deviations that may indicate a problem. Z-score. This method identifies outliers based on how many standard deviations a data point is from the mean. Time series analysis. Moving averages. We use moving averages to smooth out short-term fluctuations and highlight longer-term trends. Differencing. This technique helps detect sudden changes in data by analyzing the difference between consecutive data points. These methods are computationally efficient and effective for detecting immediate issues. We implement these algorithms using Node-RED function nodes, where we write custom JavaScript code tailored to our specific needs. When appropriate, we incorporate existing NPM packages that are compatible with our resource constraints, ensuring that we leverage proven solutions while maintaining performance. There are important considerations in deploying anomaly detection at the edge. Resource constraints. We must keep algorithms lightweight to avoid overloading the edge device. This involves optimizing code and possibly simplifying models. False positives/negatives. Tuning the algorithms is crucial to balance sensitivity and specificity. We aim to minimize false alarms while ensuring that true anomalies are detected promptly. Model updates. Our system allows for dynamic adjustment of parameters based on operational feedback. This adaptability ensures that the detection algorithms remain effective over time, even as conditions change. In the cloud, we have access to greater computational resources, allowing us to employ more complex anomaly detection methods. Machine learning models. We utilize advanced models such as neural networks, clustering algorithms, and other sophisticated techniques to detect patterns and anomalies that may not be apparent through statistical methods alone. Data aggregation. By analyzing data across multiple devices and sources, we can identify system-wide patterns and correlations, enhancing our ability to predict and detect anomalies. When critical anomalies are detected at the edge, immediate action is necessary. Immediate notifications. The edge device can trigger alerts without waiting for cloud processing, which is vital for time-sensitive issues. Methods. We publish alerts to specific MQTT topics dedicated to urgent notifications. Alternatively, the edge device can send HTTP requests to alert APIs, integrating with existing alerting systems. This immediate response capability enhances safety and reduces potential downtime. In the cloud, alerts are generated based on aggregated data and more comprehensive analysis. Aggregation and analysis. The cloud can identify anomalies that are only apparent when viewing data from multiple devices or over longer time periods. Notification channels. We utilize various channels such as email, SMS, push notifications, and integrations with messaging apps like Slack or Microsoft Teams to ensure that alerts reach the appropriate personnel. Integration with Grafana. Within Grafana dashboards, we configure alert rules that monitor specific metrics and thresholds. Grafana's built-in notification channels are used to disseminate alerts effectively. To manage alerts effectively, we implement several key practices. Alert prioritization. Alerts are categorized by severity levels, such as critical, warning, and informational. This helps recipients understand the urgency and respond appropriately. Escalation policies. We define clear procedures for handling alerts, including acknowledgement requirements and escalation paths if issues are not resolved within predefined time frames. Audit trails. All alert events are logged meticulously. This not only aids in compliance reporting but also provides valuable data for analyzing system performance and improving future responses. Now, we'll delve into how we handle data storage and management within our hybrid edge cloud system. Effective data storage solutions are critical for ensuring data integrity, availability, and scalability, which are essential for real-time analytics and long-term strategic decision-making. On our edge devices, where resources are limited, choosing the right database is crucial for performance and reliability. We consider two primary options: lightweight and file-based. SQLite is a compact, file-based database that requires minimal configuration and resources. Ideal for simple data logging. It's perfect for straightforward logging tasks where complex querying isn't necessary. InfluxDB. Optimized for time series data. InfluxDB is designed specifically for handling timestamped data, making it ideal for sensor readings. Advanced features. It offers retention policies and data downsampling, which help manage data volume over time. The choice between SQLite and InfluxDB depends on the specific needs of each deployment, such as the volume of data, required query complexity, and available system resources. To manage storage effectively on edge devices, we implement data retention strategies. Retention policies. We set policies to automatically delete or archive old data after a certain period. This prevents the database from growing indefinitely and consuming all available storage. Data compaction and compression. If supported by the database, we configure compaction and compression to reduce the storage footprint of the data. By proactively managing data retention, we ensure that the edge devices operate efficiently without running into storage limitations. Active storage management is essential to maintain system reliability. Disk usage monitoring. We continuously monitor the storage utilization on edge devices to track how much space is being used. Alerts for low storage. Automated alerts notify us when storage levels reach critical thresholds, allowing us to take action before it affects system performance. This approach helps prevent unexpected downtime and ensures that the edge devices continue to function optimally. In the cloud, we have access to a variety of scalable and robust storage solutions to handle different types of data. Relational databases. Examples: PostgreSQL, MySQL. Use case: ideal for structured data that requires complex queries and transactions. Benefits: strong data integrity, support for relational operations, and adherence to ACID properties. Time series databases. Examples: InfluxDB Cloud, AWS TimeStream. Use case: suited for high-volume sensor data with time stamps. Benefits: optimized for time series data, offering efficient storage and retrieval of sequential data points. NoSQL databases. Examples: DynamoDB, MongoDB. Use case: suitable for flexible schemas and unstructured data. Benefits: high scalability and performance, ability to handle large volumes of data without predefined schemas. By selecting the appropriate database type for each data category, we optimize performance and cost-effectiveness in the cloud environment. For storing large datasets and unstructured data, we utilize a data lake approach. Object Storage Services. Services like AWS S3 provide scalable, durable, and cost-effective storage solutions. Flexible data ingestion. We can store raw data in its native format, whether it's structured, semi-structured, or unstructured. Advanced analytics support. A data lake allows us to perform big data analytics, machine learning, and real-time processing using the vast amounts of historical data collected. This strategy ensures that we have a comprehensive repository of data to support current and future analytical needs. Effective data management requires well-defined lifecycle policies. Retention, archiving, and deletion. We establish clear policies that dictate how long data is kept, when it is archived, and when it should be deleted. Automated enforcement. Using automated tools, we enforce these policies consistently across all data stores, reducing the risk of human error. By managing the data lifecycle proactively, we optimize storage costs and ensure compliance with regulatory requirements. Safeguarding data is paramount. Regular backups. We schedule regular backups of critical data to protect against data loss due to hardware failures, software bugs, or other unforeseen events. Recovery procedures. We periodically test our recovery procedures to ensure that data can be restored quickly and accurately when needed. Disaster recovery planning. By having a solid backup and recovery strategy, we minimize downtime and maintain business continuity. Maintaining high data quality and security is essential. Data validation and cleansing. We implement processes to ensure that the data collected is accurate, consistent, and free of errors. Access controls. Strict access controls are enforced to ensure that only authorized personnel can access sensitive data, protecting against unauthorized use or breaches. Auditing and compliance. We maintain detailed audit logs to track data access and modifications, supporting compliance with regulations like GDPR or industry-specific standards. Strong data governance practices enhance trust in our data and reduce risks associated with data handling. Next, we'll explore the strategies we've employed to optimize the performance of our hybrid edge cloud system. Ensuring that both edge devices and applications run efficiently is crucial for maintaining responsiveness, reliability, and scalability, especially in resource-constrained environments. First, we focus on monitoring the resources of our edge devices. We use tools like TOP, and Node-RED's built-in monitoring nodes to keep a close eye on CPU, memory, and disk usage. By continuously monitoring these metrics, we can identify performance bottlenecks, detect unusual activity, and make informed decisions about resource allocation and optimization. Effective process management is essential for maintaining system stability. We prioritize critical processes to ensure they receive the necessary resources to function optimally. Additionally, we limit the number of concurrent processes running on the edge device. This prevents resource contention and reduces the risk of system overload, ensuring that essential tasks are not disrupted. Optimizing our code is another key aspect of performance enhancement. We focus on algorithm optimization. We refine algorithms to improve execution speed and reduce resource consumption. This involves selecting efficient algorithms and data structures suited for our specific tasks. Memory management. We carefully manage resources to avoid memory leaks and ensure that memory is released when no longer needed. This is crucial for long-term stability in systems that run continuously. These practices help us make the most of the limited resources available on edge devices. We also tune the operating system to better suit our needs. Disabling unnecessary services. By turning off services that are not required for our application, we free up system resources and reduce potential security vulnerabilities. Adjusting system parameters. We modify system settings, such as network buffer sizes, to optimize performance for our specific use cases. This fine-tuning helps improve network throughput and responsiveness. At the application level, we implement asynchronous processing to enhance performance. Non-blocking I/O operations. By using non-blocking input-output operations, we prevent the application from being held up by slow tasks. This ensures that the system remains responsive even when handling multiple operations. Callbacks and promises. In our JavaScript code, we utilize callbacks and promises to manage asynchronous tasks effectively. This allows the application to continue processing other tasks while waiting for operations to complete. We employ batch processing techniques to reduce overhead. Grouping data. By processing data in groups rather than individually, we decrease the number of processing cycles required, improving efficiency. Scheduling intensive tasks. We schedule resource-intensive tasks during periods of low system load. This ensures that critical real-time operations are not impacted by heavy processing demands. Caching is another powerful optimization strategy. In memory caching, we store frequently accessed data in memory, significantly reducing access times compared to disk reads. Efficient data structures. We use data structures that are optimized for quick retrieval and minimal memory usage, further enhancing application performance. Optimizing network communication is critical for both performance and reliability. MQTT over TCP. We use MQTT over TCP for reliable and efficient communication between the edge and the cloud. MQTT's lightweight protocol reduces overhead and is well suited for networks with limited bandwidth. Data compression. We compress data payloads before transmission. This reduces the amount of data sent over the network, decreasing transmission times and bandwidth usage. To prevent network congestion, we implement data throttling techniques. Rate limiting. We control the rate at which data is sent over the network, preventing overload and ensuring fair usage of network resources. Prioritization of critical data. We prioritize the transmission of critical data, such as alerts or time-sensitive sensor readings. This ensures that the most important information is communicated promptly, even under constrained network conditions. In this part of the presentation, we'll delve into the critical network considerations that ensure our hybrid edge cloud system operates efficiently and reliably. We'll discuss strategies for optimizing bandwidth usage and handling offline scenarios to maintain seamless data flow, even in challenging network conditions. Effective bandwidth optimization begins with reducing the amount of data transmitted over the network. Here are the key data reduction techniques we employ. Data compression. We use compression algorithms like gzip to reduce the size of data payloads before transmission. This significantly decreases the bandwidth required for data transfer. Compression is applied selectively based on data size. Large datasets benefit the most, while small messages may not require compression due to the overhead involved. Data aggregation. We combine multiple data points into a single message whenever possible. By aggregating data, we reduce the number of transmissions and the associated protocol overhead. In cases where detailed data isn't necessary, we use summaries or statistical representations, like averages or totals, to convey essential information efficiently. Edge filtering. At the edge device, we filter out irrelevant or redundant data. This ensures that only meaningful and necessary information is sent over the network. Implementing change detection algorithms allows the system to transmit data only when significant changes occur, further reducing unnecessary network traffic. Optimizing the communication protocols themselves is equally important for bandwidth efficiency. Efficient protocols. We utilize MQTT due to its low overhead and efficient bandwidth usage. MQTT is designed for lightweight communication, making it ideal for IoT applications like ours. By adjusting MQTT settings, such as keep alive intervals and payload sizes, we tailor the protocol to our specific network conditions, enhancing performance. Quality of service (QoS) levels. MQTT offers different QoS levels to balance reliability and bandwidth. QoS 0, at most once, delivery, suitable for non-critical data where minimal bandwidth usage is preferred. QoS 1, at least once, delivery, ensuring that messages are received but potentially duplicated. QoS 2, exactly once, delivery, the highest level of reliability used for critical data. We select appropriate QoS levels based on the importance of the data, maintaining a balance between transmission reliability and efficient bandwidth utilization. Network disruptions are inevitable, especially in industrial environments. Our system is designed to handle offline scenarios gracefully through local buffering. Queue mechanisms. We implement message queues on the edge devices to store data during network outages. This ensures that no data is lost when connectivity is interrupted. By using durable storage, such as writing to disk or non-volatile memory, we prevent data loss even in the event of a power failure. Retry logic. The system employs exponential back-off strategies for reconnection attempts. After each failed attempt, the wait time before the next attempt increases, reducing unnecessary network traffic and conserving resources. Continuous monitoring of network status allows the system to adapt its transmission strategies dynamically, resuming normal operations once connectivity is restored. To maintain essential functionality during network issues, we implement graceful degradation strategies. Operational modes. The system defines different modes of operation. Online mode, full functionality with real-time data transmission to the cloud. Offline mode, edge devices operate independently, storing data locally until connectivity is restored. Degraded mode, limited functionality, prioritizing critical operations while conserving resources. The system automatically adjusts its behavior based on connectivity status, ensuring that critical processes continue without interruption. User notifications. We provide clear status indicators in user interfaces to inform users of connectivity issues. Notifications enable users and administrators to be aware of network conditions, facilitating timely intervention if necessary. After a network outage, it's crucial to synchronize the buffered data with the cloud effectively. Conflict resolution. We implement strategies to handle potential data conflicts when resynchronizing. Using timestamps and versioning ensures data integrity, allowing the system to reconcile differences and maintain an accurate record of events. Bandwidth management. To prevent network congestion upon reconnection, we schedule data uploads during periods of low network usage whenever possible. The system prioritizes the transmission of critical data over less important information, ensuring that essential updates are communicated first. Rate limiting controls the flow of data, preventing sudden spikes in network traffic that could disrupt other operations. This brings us to the end of our presentation. We've journeyed through the intricacies of our hybrid edge cloud computing system, from the overall architecture and software stack to data acquisition, processing, storage, performance optimization, and finally, network considerations. Our solution is designed with a focus on efficiency, scalability, and reliability, leveraging industry best practices to meet the demanding needs of modern industrial applications. Thank you for your time and attention. We're now happy to answer any questions you may have.